Core configurations. In the world of computer hardware, core configuration refers to the physical architecture and the internal layout of the central processing unit. As a technician, understanding how these cores interact is vital for diagnosing performance issues, especially when a system feels sluggish despite having high-end specs. Single-core versus multi-core architecture. In the early days of computing, all processors were single-core, meaning they could only execute one instruction at a time. To make a computer faster, manufacturers simply increased the clock speed, the gigahertz. However, they eventually hit a thermal wall where higher speeds created too much heat for the silicon to survive. To solve this, engineers began placing multiple independent processing units, cores, onto a single piece of silicon. Dual-core/quad-core. These are common in office laptops and basic workstations. They allow the computer to handle multiple tasks simultaneously, like running a virus scan in the background while you type a document. High core count, HEDT server. High-end desktop and server processors can have 16, 32, or even 128 cores. These are designed for the heavy lifting you might do in your home lab, such as hosting multiple virtual machines or compiling massive amounts of code. Multi-threading and logical processors. While cores refer to the physical hardware, threads refer to the virtual sequences of instructions. Most modern processors utilize a technology called multi-threading. Intel calls this hyper-threading. This technology allows a single physical core to act as two logical cores. It does this by keeping a second set of instructions ready to go the instant the first set pauses to wait for data from the RAM. Technician's tip: when you open the Task Manager in Windows and see 16 graphs for an 8-core processor, you are looking at 8 physical cores and 16 logical threads. Shared versus dedicated resources, the cache. The performance of a core configuration isn't just about the number of cores, it's about how they talk to each other. This is where the CPU cache comes in. The cache is a tiny amount of incredibly fast memory located right on the processor die. L1 cache, the smallest and fastest, dedicated to each individual core. L2 cache, slightly larger, often shared between a pair of cores. L3 cache, the largest, usually shared across the entire processor. It acts as a massive pool of data that all cores can dip into, which is essential for gaming and complex AI simulations. P-cores and E-cores, hybrid architecture. In recent years, especially with Intel's newer generations, we've seen a shift toward hybrid core configurations. Instead of making all cores identical, the processor uses two different types. Performance cores, P-cores. These are physically large, high-power cores designed for heavy tasks like gaming or video rendering. Efficient cores, E-cores. These are smaller and use much less power. They handle background tasks like Windows updates or browser tabs, allowing the P-cores to focus entirely on the user's primary task. This configuration is particularly useful for maximizing battery life in laptops, while still providing burst power when needed.